Okay, now, before we just start to just go ahead to just do some kind of fun and interesting Bayesian data analysis, the thing that I just want to do is just to do some very basic and elementary explanations of what's going to be your plan. And then when we just run the codes, you understand every single bit of the code which is going to be run in the R environment. You remember from our previous discussions, we talked about a type of the datasets. That datasets was called the women. And in that datasets, we had, if I can just draw it in a kind of a plot, if I can plot that datasets. You remember that, for example, if we imagine that we have two axes, one of them, I said that it's going to represent the height, and one of them is going to represent, let's say, the weight. In the discussion that we had, we showed that essentially that the data that we had, we could have looked at it as a kind of a normal distribution. And we had essentially in that analysis, we had somehow a sort of a mean. We call that nu W for the weight. And also we had a corresponding value on the height axis. And also we had, for example, those tails of our modeling of our datasets as a normal distribution. In the previous discussions that we had, we said that, imagine that we can just follow a simple, I'm just going to call that a non-Bayesian essentially. In the non-Bayesian frameworks that we talked about, that I should say, on the previous, discussions, we said that imagine that we just want to follow these simple expressions that y equals to ax plus b is going to be mimicked by the heights and the weights of those women. Essentially, what did we mean was that, imagine that we said that the height is going to be represented as a slope A times weight plus an intercept B. That was a thing that we talked about that when we were talking about the non-Bayesian frameworks in our modeling that we had before. In our discussions, the thing that we talked was that we are looking for making an inference about A and B, which is going to be our intercepts and the slope of our model, and the best estimates of these A and B made us enable to make some predictions if, let's say, a 16 woman joins in our datasets, and if we know how much its weight, then we were able to make a prediction about its or her height in our model that we had. It was something very interesting that we did. However, in our Bayesian analysis, imagine that we just follow a simple procedure so closely related to the thing that we just did before, but I'm just going to call that here, it's going to be a Bayesian, I should say, structures that we are just going to follow. In the Bayesian structures that we're going to have, we are going to come here and very simply write a simple notations of, for example, the inferences that we're just going to have. Imagine that we say that the volume that we are just going to represent is going to right now is going to be represented now as a distributions of a normal, let's say, the distribution. I'm just going to call that normal with mu and sigma, which based on the basic understanding that we have made so far in our statistics, we know that the nu is going to be the mean and sigma is going to be the standard deviation, which shows that how far we are away from, for example, from the mean, from any data sets that we have. And now, in these representations that we had for the y, imagine that if our y is going to be represented at what? In this case, we said that because we were trying to model the height as a function of the weight, we are going to say that, okay, the height of those American women that we are just going to represent, it's essentially as a normal distribution of a nu, which is the nu which we have is going to be, I should say, the nu is the average of the heights, and also besides from the nu, we have also the sigma, which is going to be our standard deviations of the model that we have. However, the thing that we are just going to do is that it's becoming very simple, and now we are just going to come and say that, okay, in our model, we are going to look at the nu, and we call that a parameter. For example, sometimes you say that in your normal distribution, for example, you just come and say, for example, the height. I'm just going to write it a little bit on top. It's a normal distribution, for example, of the mean of the height. Let's say we call that the mean is going to be 165 centimeter, and we have a standard deviation of 15, for example, centimeters. Then you can just come up with an infinite number of the points in our plane that it represents the height, which is described by this simple, I should say, simple representation, which is going to be a normal distribution. We can come here and say that, okay, the mean heights of the people in our data sets is going to be 165 centimeters, which they are either 15 centimeters taller, which it can be from probably, let's say, the maximum height. It can be represented by 180, and we can sometimes we have the people in our data sets, which is going to be, let's say, 150, which is going to be minus 15 standard deviations from the mean of those heights in our data sets. In these representations that we had, everything is very clear, because we know what is going to be the mean height and what is going to be the standard deviations from that mean height. Then we can just have a kind of a normal distribution which represents those kind of characteristic parameters in our normal distribution, which is the mean and standard deviation. However, imagine that we just come in our model, say, okay, our standard deviation, let's say, is going to be represented as, let's say, 20 centimeters. However, the mean of the heights in our model is not going to be explicitly emphasized. And we are just going to represent the population's height. For example, imagine that. Still, we are talking about the height of those 15 American women, which they were aged from 30 to 39. And we say that, okay, we are not going to explicitly define the mean height which they have. However, instead of explicitly defining it, we are just going to show that by a parameter. That's what I call the parameter. Then essentially, I'm just going to go to the next page to write my stuff there. And I say that, okay, in that case, the thing that we saw, we said that the height of those American women is a distribution which is normal. However, in that normal distribution, I do not explicitly define, I should say, mu, which is going to be the average height of those women. But I just come here and say that, okay, for example, 15 centimeter is going to be the standard deviation away from the mean height of those women on my data sets. Then essentially, what we saw that as a result that because nu is a parameter, we call that a parametric Bayesian analysis. That's why we call that this is going to be a parametric Bayesian analysis. Because instead of explicitly defining the value of the average height, we just introduce a parameter. However, things are going to get more interesting. And for the parameter that we define on top, we are just going to come say, okay, the parameter which I defined, which it was nu, it itself is going to be modeled. And it's going to be modeled in a sense that I'm just going to say the model is going to be ax plus b. What is going to be the x for us here? As what you have seen in our the discussions that we had on the non-Bayesian analysis, you saw that the x here can represent the women's weight. Then we say that the nu is going to be represented essentially as this. The nu is going to be essentially represented as the a into the women's weight plus the intercept b. And that's essentially is the building blocks of the codes that we are just going to run in our next tutorials. Then we come here in our analysis, define the distribution of the heights, which we take it as a normal distribution, but instead of explicitly defining the mean heights of those American women, we define the mean as a single variable model, which is going to be ax plus b. And the thing that we are just going to do in the Bayesian inference that we're just going to make in the next tutorials, we are looking for the best estimates that we can think of. Let's say, for example, the best estimates that we can think of the a and the b, and we're just going to compare these two values with the inferences that we have made with the non-Bayesian data analysis that we did on the same type of the data sets on our previous tutorials. Then essentially that's going to be our roadmap that we are just going to do that in our next tutorials then. However, as you will see, we have only one single variable, which is going to be the x in our model then. On the next tutorials, I'm just going to talk about more about the specificity and some kind of tricks that we're just going to encounter. But before we do that, on the next tutorials, I'm just going to talk about one more technique in our Bayesian data analysis, which is going to be talking about the priors distribution when we just run our model. I see you on the next tutorial.